So in my package specification, I declare my string is in use, pass in the value or the name, return true or false. Mark a string is being used, pass in the value, and mark it as being used. How do I do that? Well, inside my package body, I have a list of string names indexed by PLS integer. This variable name, by the way, is a subtype. It's a type based on another type. And I basically just hide the fact that it's a varchar2, give it an application-specific name. This holds a variable name, and that makes my code, I think, a little bit easier to understand. So it's a list of variable names indexed by integer. To mark a string as being used, I take that value and I add it to my list. I get the current number of elements defined in my list, and I add one to it. So every time I generate a new declaration, it first puts it in the index position 1, then 2, then 3, then 4. It sequentially fills the collection. So I've got my sequentially filled collection of used names. Now I need to figure out if a string or if a variable name is in use. How do I do that? Well, I get the total number of elements defined in my collection. I get the lowest or first defined element. That should be 1, pretty much always 1 unless it's empty. I have a Boolean flag to indicate whether or not I found a match. And as long as I haven't found a match, and there's another index, another element that I haven't looked at yet, check to see if that current index finds a name that's equal to the name I passed in. If I found a match, then I stop and return that index, or return true that I found a match. Otherwise, I keep looking. And if I go through the whole list, in other words, if this variable is not in the list yet, then the loop terminates without setting found to true, and it returns false. Wow. Well, that's probably not very difficult for you to understand. It's not a very complicated program, but it's still, let's see, 15 lines of code that I have to write, code that I have to debug, code that it took a while to explain to you. So that's kind of a drag that I have to write all that code, but look, if you have to do it, you have to do it. And the question is, do I really have to do that? And what are the potential problems with this program? Now, the fact is, we don't have to write all this code to achieve the goal, and I'll show you how to do it with string indexing in a much simpler way. But first, let me ask the question of what's wrong with this code. Suppose that it works. I believe that it does work. It's a bug-free piece of code. Is it the ideal solution? And the answer is that it has a pretty big problem. As my collection, my list of names gets bigger and bigger and bigger, the search through this collection to see whether or not the name was used, and obviously what I mostly want to know is that the name is not used, and in fact, almost always it will return false. The name is not used yet. It's going to take longer and longer to get that answer. Yes, this variable name is okay, generate it, as my list gets longer and longer. This is not a data neutral algorithm. In general, you're best off by writing programs whose performance does not vary greatly depending on the range of data, the types of different data scenarios that are handed to it. If you write programs that get slower and slower and slower as your data volume increases, then usually what that means is you have an application that gets slower and slower and slower as your application ages and the volume of data grows. So this is a suboptimal implementation in a number of ways. It's a fair amount of code to build, maintain, and explain, and it's not always going to necessarily be fast enough to meet production requirements. And the question is there a better way? And the answer is absolutely. And the way to do it, the way to get around these problems and come up with a much simpler implementation, is to use string indexing. So let's take a look at my string tracker 1 package, and I'll explain everything you see on the page here. Whoops. Now in string tracker 1, the package specification is exactly the same as it was before. Mark a string is being used, is a string in use. But the package body is quite different. Now previously what I had was a single indexed integer index collection, and I populated the collection sequentially. In my second attempt at building this package, things are different. Now my list of used elements is a table of does not matter, indexed by variable name. Okay, so the first thing to recognize is that I'm now indexing by string. I'm indexing, in fact, by the variable name. Table of does not matter, what is all that about? Well, does not matter is a subtype. Basically, it's another name for Boolean. And what I've done here is try to self-document how my code is going to work. And what I'm doing is giving you a warning that it really doesn't matter what value goes into this collection. And as you're about to see, that is absolutely the case. So I've got my string index collection of booleans. I declare my variable based on that type. Let's take a look at mark as used. Now previously mark as used was one line of code, assign that value to my collection. Very simple. In string tracker version 1, it's still one line of code, but it's different. Now I take that variable name, I use it as the index value in my collection, and I assign a value of does not matter to that location. Does not matter is null. And the point here is that it really doesn't matter what's in the collection because I never look at the value at a particular index value. I never look at the element at an index value. I'm only going to use the index value, as you're about to see. But first of all, notice that I'm using the variable name itself as the index. Okay, now let's take a look at string in use. I pass in the variable name. And to find out whether or not the string is already in use, all I have to do is use the exists method, go to that location and ask, does an element already exist for this variable name? If so, return true. If not, return false. So notice, I never actually look at the element, the value, which is always null in this case. But it could be true or false or a date or a string. It really doesn't matter. I just want to know, is the element defined? And what I've done here is taken a big algorithm, a bunch of code that I not only have to write and sort out and debug, but that also gets slower and slower as the array gets bigger and bigger. I convert that to a single line of code whose performance is the same regardless of how big the collection is. So this is, I think, the clearest, simplest example I can give you of the elegance and the power of a string index collection. And essentially, what you want to do is look for places in your code where you're starting to use collections, and the first impression or the first approach that we generally take is to use sequentially allocated lists. Put something in row 1, then in row 2, then in row 3. And when we do that, sometimes it's a perfect fit for what we need. But in cases like this, we end up writing code that involves looping through the collection. So if you find yourself populating a collection in a certain way, and then needing to iterate through the collection, essentially doing a full collection scan, looking for a match on one kind of data or another, ask yourself, maybe I should change the way I'm indexing this collection. Maybe I should change to a string index. And then I can get rid of all that searching code, let Oracle do the work for me. And sometimes you might even find the need to create multiple collections that provide indexing into this collection, in which case you should take a look at my video on non-sequential indexing in associative arrays, in which I explore that particular idea specifically under the topic of emulating unique indexes in associative arrays. But here the main thing to keep in mind is if you find yourself iterating through your collection looking for a string match, then maybe you should switch to a string index collection and make all that code go away, make your code more efficient. Let's talk about another topic that might arise that's relevant to string indexing, and that's when you might want to convert from integer indexing to string indexing. Suppose that I decided to emulate my primary key in a collection index for a batch job. So again, this topic is covered in great detail in the non-sequential indexing lesson in collections, and it demonstrates how you can get much better performance by querying the data down from the database into a collection, using the primary key as an index, and then being able to look up rows of information with the primary key much, much faster, order of magnitude or more, than querying over and over again. So I built this batch job. It's running super fast. It's really great. But the problem is that my primary key values are approaching 2 to the 31st minus 1. That's the maximum allowed in a collection, about 2.14 billion. Obviously, not all of our tables are that big, but some of them are. And if you have sequence-generated primary keys, you could be running into this problem. So, if I have an integer index, as soon as I hit that limit, I'm going to run into a problem. I'm going to get errors from Oracle. And the question is, do I have to abandon this entire technique, throw out the collection, go back to querying all my rows and endure all the overhead slowing down my batch job? And the answer is no. You don't have to do that. What you can do is simply convert to a string index. With a string index, you don't have to worry about the size, or the actual value hitting the limit. You have to worry about the number of elements defined in the collection. Sorry about the little typo there. I'll fix it up really soon. So you only have to worry about actually hitting the limit of 2 to the 31st minus 1 elements, or actually 2 times 2 to the 31st minus 1 elements. Lots and lots of elements. So you're likely to run out of memory before that ever happens, and you can completely avoid the problem of hitting the maximum value. Let's take a look at a script that demonstrates what I'm talking about here. First of all, in terms of emulating the primary key, here's an example of a script that does that. So I create a collection that has the same structure as the employees table. My function oneRow returns a row for the primary key, and all I have to do is go to that location in my cache and return it. And the way I do that is when I populate my collection, I use the primary key as the row number. So very powerful technique, gives you much faster access to repetitive retrievals of the same data. The problem is my employee ID might hit that limit of 2 to the 31st minus 1. If it's starting to get close, what I can do is something like this. Here's my integer to string indexing script. And what I'm going to do is switch between integer and string indexing and see what the impact is. And how I'm doing that in this case is using conditional compilation. This is a relatively new and advanced feature of PL/SQL, in which I can specify through flag values which one I should use. So if I'm using an integer index, use PLS integer. Otherwise, use varchar2 32k. This is not at a point at which I can demonstrate all these different elements of this code to you in terms of how the conditional compilation works. It'll be available under the effective management of PL/SQL code. But here's an example of setting my PL/SQL flags. So by default, integer index is null. Oh, sorry, I set it to true here. So when I compile this code, it'll use the integer index. And then what I'm going to do is populate my collection of data, and then see if I get an error if it reaches the limit. So notice I'm going to pass in 2 to the 31st minus 1, and then it's going to go through a number of iterations of assigning values to that collection past the limit. And then we'll see if an error is raised and what kind of error message it is. So that's for my integer indexing. And then I'm going to convert to non-integer indexing. I'm going to specify false. It's going to redefine this procedure using varchar2 as my index by type. So this will all be ignored, and it'll simply index by varchar2 automatically. And then I'll try it again. And I'll start with 2 to the 31st minus 1. That's the upper limit on an index value. And I'll add values to it. Notice the shift by. And so it'll again go past the limit, and we'll see if I get an error. I run my script. Let's first clear out any output I've got here. Okay. I run my script. And here's what I see. Load employees into cache indexed by PLS integer. Try to load employee to index 2.1, etc. Numeric overflow. So as soon as I tried to use an index value that was past the limit, Oracle said, no, you can't do that. You get a numeric overflow error. Now I converted to a cache indexed by varchar2. And notice, I have no problem using all these index values that are well beyond 2 to the 31st minus 1. Because what's going on is that since I've indexed by string, when I use this index value right here to populate my element in my array, Oracle is implicitly converting this integer to a string. The string is used as my index value. And then under the covers, Oracle takes that string, which is this number. This is a string, not a number. It takes that string, which is certainly not too large, and converts it into an integer in the valid range of values, and then allows me to use it. So the bottom line is that if you have decided to use this primary key or a unique index emulation, and you ever find yourself reaching that upper limit of 2 to the 31st minus 1, do not panic. Do not throw away all your code and rewrite it and avoid using collections. It is usually possible to simply switch from integer indexing to string, and all your problems will go away. And again, because those numbers, while they're really big integer values, are really small strings, the number of characters in these integer values is really quite small. The cost of doing the conversion from string to integer is not going to be significant. You can probably you may not notice any impact on performance at all. Certainly, it's still going to be much, much faster than querying the data from the database over and over and over again. All right, some key lessons and to look ahead. String indexing in an associative array greatly extends the usefulness of the data type. You can index by just about any data or combination of data as long as you can convert it to a string. It's especially useful when you're emulating unique indexes in relational tables, because those unique indexes are not always just a bunch of integer values. They can be strings, combinations of different columns, and so forth. So you can get a tremendous amount of benefit from the string indexing. And in general, the key thing to look for in your code is that if you find yourself performing full collection scans, consider changing your indexing approach. So don't search through a collection to find a match for a string or a date and so on. Instead, recreate the collection with a different type of index, a string index collection, or create a separate collection whose only purpose is to provide an index into the main collection using a string indexing on the value that you want to find a match on. Either way, you'll avoid the full collection scans and have code that's much faster in general, and certainly as your data volume increases. Looking ahead, the next major advanced topic to cover in collections is multi-level or nested collections, which I think is about the most complicated feature I've ever used inside PLSQL. So I encourage you to make sure that you go back over the other lessons on associative arrays in particular, methods, working with associative arrays, non-sequential indexing, and also now the string index collections. Make sure that these are all very clear to you, comfortable to you, before you move on to nested collections. And finally, I do encourage you to go back through this video, download my demo zip, and play around with each of the scripts that I talk about in this lesson, because there's a lot of really interesting and complex functionality going on. And I can only get across to you so much in a video. You have to actually run the code, play with it, try it out yourself. And then you'll really have internalized it and able to put it to great use in your own applications. So I hope this was useful to you, and hopefully you can put it to work in your applications quickly and in many different places. So happy PL SQL coding.